Okay. Do you listen me? In the virtual classroom, can you listen me? Okay. Do you see the board? So you can see the slides, right? Perfect. So if we are everyone here, I think that we can close the door. Everyone take a seat. Okay. This is the first lab of digital electronic design. That's right. Are you here for this? Okay. So in the first lab, we will examine a brief overview of the main tools that we will use in this course. Okay, since we are a lot, and especially we have two rounds of labs, I will suggest you start preparing all the environment that we need for the next labs. And this lesson is dedicated to this. Of course, if there are any troubles or problems with the installation and so on, you can write to me. This is my mail. And I can just tell you that I don't know if you have seen the advice on the portal. There was a couple of links to download the tools. Does anyone do this? Okay. Did you have a problem? No, fine. Okay. So the first tools that we will see is the digital. Digital is a software made for digital electronic circuits to simulate it. And I will show you a brief example of a small circuit, digital circuit, to see how it behaves and the main skills that this software has. Then we will go through with the Quartus setup environment, which is the most easy part. Does any one of you have MacBook? Okay, few. And have you tried to install the Quartus environment? Pardon? Okay, so sorry. So you was able to run it? Okay, that's fine. That's perfect. Because the last year we had a lot of trouble with this. So if someone has trouble, go to him. Okay. In any case, if someone of you has other troubles, you can again write to me, or you can. Okay, maybe we don't have the microphone. I hope that you can listen to me in any way. Do you listen me? I know. If there are any other troubles, I suggest you to form a little groups with people who have the whole environment fine. And in this way, you should go on with the lab and so on. So let's start. What is digital? Digital is a simple simulator used to simulate digital circuits, as I told you. In particular, you will see in the lessons a lot of devices and small elements that can be modeled in different way. And with this tool, you can simulate the circuit, and also you can see how it behaves. So the waveform of the signals, the timing, the stops, and so on. So all the logic gate can be connected with wires as in the real life, and the overall behavior can be simulated. There are also buttons that can simulate the testing, the switch on, the switch off of the circuit, and so on. Now we'll show you. Then the Quartus Lite is the main environment and software that we will use for FPGA. Does anyone of you knows what is an FPGA? I guess maybe yes, maybe no, because you are informatics, right? Okay. It's an hardware device that can be programmable. This means that inside of him you can put software coded in a particular languages. In this case, in this course, we will see Verilog. It's more or less like C++, more or less, and can be customized and programmed to design and support different kind of circuits. So Quartus can create the environment and has all the tools for logic design, project management, compilation, and timing analysis. Then there is Verilog. Verilog is on the other side, the open source compiler. So as you use the compiler from Python for other kind of Java and so on, you have Verilog. And it's the hardware description language. It's designed to translate Verilog into a netlist and so simulate the hardware design, because of course we have to translate in a code what is the hardware. So how many inputs the hardware can have, the output, what they have to do, and so on. Of course, there are multiple platforms that can run this, such as Linux, Windows, and Mac. And then we have GTK Plus or Wave, which is just a simple waveform viewer. So just a small check to see if everybody... Okay, maybe I'm not sharing the screen. Okay, fine. Maybe now. But I don't know how to see multiple. Now you see it from the web. Okay, perfect. If you can, just speak to me and tell me what happened, because I'm switched to the board, so I don't know what you are seeing. So this is just the first. This was the first. This is the second. It's just written what I have already told you. So digital, Quartus Lite, Verilog, and GTK Plus. So now we move on digital tool demo. It's what I prepare for you to show you how it works. I don't know if in the following labs you will see it properly doing some kind of exercise, but in any case, I will show you how it works. So you can download it from this repository on GitHub, and I suggest you to do it if you want to try. It's pretty easy. You have just to download the folder, and then inside there are other folders. In some of them, there is a folder with some exercises, and one of them I will show you today. And then there is the Excel file that you run, and the software will go on. Did you already install it? Every one of you? Pardon? Yeah, it's easy. So there is also some kind of instruction if you have a multi-file project. I don't think that this will be our case right now, but just to let you know, you can use multiple files to run different kind of circuit that maybe are embedded in one more complex. And in this case, you just have to be sure that the names are not equal, so that there could be ambiguities, and everything is loaded not in a path, but just in a folder, and digital will search all the files that it needs to run the circuits. Okay, I don't know if during the lessons of maybe yesterday, should be the first lesson, Professor Crovetti started talking about CMOS switches or CMOS transistor. Can you tell me yes or no? 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 Okay. Anyway, it's pretty simple. And just to introduce you this topology of devices, CMOS transistors are basically digital analog devices that can be used in digital circuits because they behave like switches. So it can be open or closed. It depends on the input that the MOS received from the gate. So I will show, it's written in the slides for people from home, but just to have more contact with you, I will show it here. Or maybe better, since we are digital, I can write it here, so that everyone can see it. This is the symbol of a transistor. Why it is designed in this way? Because in the real life, there is like a box, and in this box, there are multiple layers. In these layers, there is such kind of materials that can be drugged. What does it mean? That you can put iron or other electronics component of the material that can modify the characteristic of the natural material. In this case, you can have, since how do you drugate it, you can have two kinds of topology. You can have a PMOS or NMOS. If you don't understand something, please ask me to repeat and be more clear. So, and these two devices behaves mostly in the same way, but one is the opposite of the other. So I told you they behave like switches. So I don't know if you remember the capacitance. The capacitance could be loaded or empty. If it's loaded, it is like something in which can throw the current. If it's empty, nothing can go inside of it. In this case, it's more or less the same. If you have a switch which is on, it behaves as a closed loop, so current can go through it. If it behaves in off condition, it can behave like an open circuit, so nothing can go through it. And this is exactly how NMOS behaves. If you receive from the gate an input which is equal to 0, it behaves like an open circuit, so nothing can go inside of it. So it's just open, okay? If you receive an input which is 1, it behaves like a closed loop, so something can go through the wire, okay? Imagine like the wire is a conductive, so something can go through it. If if it's continue. If it's open, nothing can go through it. In the dual form, there is the PMOS, which behaves exactly in the opposite way. If we receive 0, it's closed, so it's on. If it's open, it's open, so nothing can go through it, it's off. These three symbols, which is G, D, and S, are three main characteristics of the transistor. There is a gate, there is a drain, so D, and there is a source, S. Typically, the current can go from the up to the down, and in this case, and nothing can go through the drain. In such kind of application like digital, you can see also two more symbols that identify NMOS and PMOS. In this case, to identify NMOS, there is just gate, drain, and source. In the PMOS, you have here a small ball which identify the opposite behavior of the transistor. In digital, you will see this, I don't know how, okay. In digital, for example, you will see another representation of the transistor symbol, which is this, with an error here. So, if it's NMOS, the arrow go inside. If it's PMOS, the arrow go outside. It's clear? Right now? Do you have question? Okay. So come back to this circuit. In this circuit, since CMOS transistors are basically switches, the first idea that you have is to put on and off a light, no? So switch on and switch off the light is the exercise that we will examine today. This is the topology of the circuit. As you can see here, we have two transistors, a PMOS and NMOS. Why two if I can use just one, right? Because I told you that one in both ways can be on and off. So why I use two of them? Because with the two of them, you have more control on the power distribution, of the power consumption, and so on of the circuit. So in digital circuits, we will usually have two parts of the circuit, pull up and pull down. What does it mean? There is a physical meaning of this. To remember it, think about PMOS pull up, PP. NMOS pull down, NN. Take the last letter. Why you don't write? Okay, N. Maybe I delete it because if not, you can read. Okay. What this physically mean? That PMOS acts as a switch to VDD. VDD here is the voltage that we have to the top of the circuit. And then NMOS acts with a switch to the ground, which is the voltage that we have to the bottom of the circuit. So now let's imagine that in the input, which I told you before, G, you receive an input which is 0. So what you will expect, that NMOS, as I told you before, will be open and a PMOS will be closed, right? So in this way, if PMOS is, I say, G as 0, okay? So NMOS is off and PMOS is on. What does it mean? That this is closed, so current can go through it. This is open, so nothing can go through it. So in this case, V out, which is the voltage here, will be equal to 0, because if here I have nothing, here the voltage is 0. In the opposite case, if I have G equal to 1, G equal to 1 means that the PMOS is off, so this is open. And if G is 1, the NMOS is closed. So here there will be a tension, and V out will be equal to VDD. Sorry, here there is a mistake, because maybe the slides are not correct. I will correct it after. So in this case, V out is 0, and in this case, V out is equal to VDD. This is simply the opposite. Sorry. Why? Because if here is closed, imagine a wire. What is the tension that go from here to here? Is as the ground, no? Because here it can't see VDD. VDD is stops here, can go through here, right? In this other case, if VDD arrives here because there is a wire to connect it, V out can see VDD. But here, the zero tension can be seen here because here stops, right? Okay, and that's why we call it pull up and pull down, because the pull up, so if the PMOS is on, we see the up voltage, VDD. If the NMOS is on, we go pull down, so we will see zero voltage. Clear? Any questions? Okay, let's move to here. Does anyone have a question from the web? I suppose not. Okay, let's go home. Yeah. Pardon? So here there is another concept. So you are asking me how I can call it 0 or 1 if there is a voltage, right? And the voltage can be from 0 to 5 volts, for example. That is the question. Oh, yes, of course, it's given. Typically, a circuit can be made with a VDD equal to 5 volts, and of course, ground is equal to 0 volts. That's given. Again? Okay, you are confusing G with the VDD, right? Do you think it's the same? Okay. I told you that a circuit has a voltage in the up, okay, which is VDD, and then there is the ground. Every circuit has an up tension and a down voltage, right? Okay. In this case, I put here another tension, which is a generator of current or voltage, whatever, okay? And this generator can go, for example, from 0 to, why? Okay. can go from 0, for example, to 3 volts, okay? So the tension is more or less as this. For a certain part is 0, for a certain part is 3, is a stepped voltage. Meanwhile, the input voltage, so in this case G, because G is a voltage, meanwhile is 0, G will be 0. Over a threshold that we call Vt, which is a characteristic of the transistor, we will have 3 volt. So if I have 3 volt as input, G will be 1. Exactly, can be something in between, but there is a voltage threshold. For example, I can have for a small time 2.1 volt, okay? But in this case, if the Vt I tell you that is 1.5, what do you think that G will be if I give you a voltage like what? Exactly. Does anyone understand this? Okay, so if the input is 0, again, I have the down voltage, so 0. If the input is 1, sorry, if the input is 1, I have the ground voltage. If it's 0, I have the VDD voltage. Any other question? So now that it's clear? Okay. Does anyone? Okay. So let's see on digital. On digital, we have a sort of screen like this, where you can add components like this, logic components, input output components, wires, flexor, flip-flop, memory, switches, and many other stuffs that you will see during the course. And here I have recreated something similar to this topology, okay? So here we have an input that can be, let's call it this way, if not is like the current. An input and the output. What will be the output? In this circuit, what is the output? What? Right, it's the light. In this case, we call it LED light. And what is the input? What? I can hear you. Yes, A. Yeah, A, but physically, what it is? Based on what I told you before, what is the input? I have told you that here I will probably introduce a generator. So what will be A? A generator. Okay. And as I told you before, the generator will give you a voltage that, for example, goes from 0 to 3 volts. It will be, the input A will be 0 if I go down to the voltage threshold. It will be 1 if I go up to the voltage threshold, okay? This voltage threshold, it's typical of the transistor. We will do exercise on it on the next exercise lesson. It depends on the material, on how it is built. So we have the LED, and here we'll have typically the generator. But in this case, since this simulator is digital, we will see A just to be 0 or 1. So this is the pull up, this is the pull down. Here, what we will have? On the down, what voltage we have? Perfect, ground. And on the up part, what we will have? Which kind of voltage? How I call it before? VDD. Okay, so it's the same as before. Now I'm just simulated it. And as I told you before, you can visualize with this tool the waveform. So for example, here we will see how A, B, and C behaves during the time. And then we have also buttons that simulate the turn on and off the circuits, not the LED, the circuits. So here we have the different case study since A can be 0 or 1. So now answer with me to make me understand that you have understand, okay? So if A is 0, what will happen? What? Tell me about the light. The light how will be? On. Perfect. And why? Yes. So the PMOS how will be? On or off? Exactly. But I should put here. Okay. On. And the NMOS how will be? If it's the opposite, remember, P and N behaves as the opposite. Okay, now let's put A as 1. As you can see here, the waveform. If A is 0, light is on, so this is up. So if now A is 1, A will be the P transistor. On or off? Exactly. And the NMOS? Exactly. As you can see here, the waveform follows this behavior of the circuit. Now there is a small time of, how'd you say, restart, setup, a meta state, and then we go on. We go on and see again A equal to 0. This is P is, if A is 0, exactly, this, exactly, perfect. Does anyone have question? Please. Pardon? Okay. Let's see it again. Put another page and explain again. So I said you that a transistor can be designed in this way, right? We have D, which is the transistor is made up of 3 parts: drain, gate, and source. Okay? So this is an NMOS, as you said before, top. And the PMOS, how is the PMOS? there is a little dot here that indicates the opposite, okay? This is the PMOS. And again, we have drain, gate, and source. I told you that if the gate is equal, I told you, let's do from the start. I told you that if the gate comes from a voltage, so in this case from can I say a generator, the voltage can go from 0 to, for example, 3 volts, okay? And this is a step voltage. So this means that we have 0 for a certain time and then goes up to 3. And here we have VT, which is voltage threshold, which is typical of the transistor. You design it specifically for the transistor. So if the voltage of the generator, voltage input, is from 0 to volt threshold, G I will be if it's from 0 to voltage threshold, how it will be 0 because it's low, okay? It's down to the voltage threshold. If we are here, so VE is between VT and 3 volts, I will be G. Exactly. So now move on. Let's suppose that G is 0. I will be the NMOS. How it behaves. Open? Exactly. So we will have something like this, no? So NMOS is off. If G is 1, the NMOS, how it will be? So current can go through him. And so it will be, okay, perfect. Now, dual form for PMOS. If G is 0, the PMOS, how it will be? Exactly. So PMOS is on. And in this other case, G is equal to 1. PMOS, how it will be? Open, perfect. This is NMOS, PMOS, sorry. PMOS, off. Clear until this point? Perfect. Tell me. Here, okay. I told you that G in the hardware cannot be 0 or 1. 0 or 1 is just a code from the informatician stuff, okay? What you will physically put there is a generator of voltage. But the generator of voltage is analog, so you will have all the values between 0 and 3 volts. So there exists a time and a case where you will have also voltage between 0 and 3, which is, for example, 2.1 or, I don't know, 1.5. And in this case, how can you translate it to 0 or 1? Exactly, there is a threshold. As a, I don't know, the sigmoid, or in informatician codifying, there is the sigmoid, right? When you have to classify something. No? No? Okay, delete it. Okay. So in any case, there is a threshold that you have to go up to have 1 and go down to have 0, okay? So let's put that this threshold is 1.5. If I'm down 1.5, what will be 0? And up So in this way, I can tell you, let's suppose that G is 0 or G is 1, because I assumed this before. Okay, this is my true input. Then I codified it in this way. And why I codified it in this way? Because the transistor behaves exactly with a voltage threshold. When it receives a voltage that is up to the voltage threshold, it for NMOS is on. If it's up, so it's on. If it's down this threshold, it can't be on. It still be off. It's like if you don't put enough current or energy in the element, it will not be on. Yes, please. It's designed specifically for the transistor. Each kind of transistor has its voltage threshold. Okay, there is every time that you buy a digital element, an analog element, a circuit component in general, you have a data sheet. In the data sheet, the manufacturer tells you this element has a 1.3 voltage threshold to be on and off. As also it will say you the dimension and all the other characteristics. Believe me, there are a lot. Okay, so everyone understand this? Okay. Now I told you, since the transistor behaves like a switches, I want to make the example of turn on and off a light. So I have a pull up here. What is the pull up? Which kind of a transistor? Exactly, up P. And here, of course, I have the dual form, which is NMOS. This is V out. Here I have V in. Here I have VDD. And here I have ground. That's fine. Did you understand this? Okay. What I have to put here to have a translation to G? Source, generator, exactly. And what I have to put out if I want to switch on and off the lights? If you want to switch on and switch off the light, can you tell him speaking or connecting him? Here there is the light. You connect to the output, the light. So now let's put that G is 0. How I can draw my circuit? Here I have anyway the generator, blah, blah, blah. Here I have VDD, and here I have the ground. Okay, and here I have the LED. How this will be if G is 0? If G is 0, the PMOS is open or closed? If G is 0, the PMOS is closed, so is on. So here I can draw a connective wire, right? And the NMOS, I will be, okay. So here was the V out, and here is the LED. What is the tension that the LED will see? What is V out? Equal to V input, okay, but V input has been used just to drive Exactly. V out is equal to VDD. And so the LED will be exactly what we said before. Exactly this. And the LED was on, right? Okay. Go on. Now let's put that G is 1. We have here VDD. We have again the source, then we have the ground, etc. Here we have the LED. If G is 1, the PMOS, how is? Exactly. And how is the NMOS? Exactly. And so what tension, what voltage will see? 0, exactly. V out is equal to 0. And so the LED will be on or off? Off? Yes, I suppose it too. So now go to the previous slide. Why is 0? Because the ground, which value has? Yeah, if you connect a tension with a wire, it will put the tension to the end of the wire, okay? So let's go to this light. Does anyone have another question here? I suppose not. That's fine. Okay. Now, just to show you that digital exists, I want to open it to you. So let's go here. Blah, blah, blah. This is the folder that you have, right? This is the X file. You run it, and that's digital. Okay? So I downloaded this circuit from exactly the folder where there are examples. And I used CMOS. I think that the name is, God. Maybe inverter. Okay, you don't want to open like this. If you go here and you go to file, if I can. Okay. File, and you go to open inverter, you will have this. So just to conclude what I explained to you right now, if I told you that this one is the opposite of this one, which logic gate reminds you? Did you see the logic gate at lesson? So, and not, or, okay, which logic gate reminds you this circuit? It's an AND. If they are the opposite of each other, which logic gates reminds you? Not. This is exactly the analog form of the NOT gate. Okay? Sorry, digital form. Okay, so always here, just to show you, this is test. I press it and I can move it. Here from components, I can choose whatever I want. For example, LED. This is the LED. But now put it in the trash. And then if you want to do the analysis and see the waveform, you go here and you run the simulation. And if you change the A, clicking on it, you can see the waveform. If just this can go, okay. And this can be done for every kind of circuits. Cool, huh? Nice. So now, since we have half of an hour, I suggest to move on to the setup of a Quartus environment. From the web, everything is fine? There are any questions? Okay, I suppose it's fine. So, here. We can go on. Quartus setup. So I told you that for the installation and the download, we have to go to this website and then obtain a license. The license can be obtained creating an account on this other link. Then you logged in again in the Intel platform, and you will be able to download the Intel Questa FPGA Starter Edition. Does anyone do this? Okay, I suggest for the other guys to do this right now because we have 30 minutes. And if you have problems or something like that, I can help you. Yeah. There is? Okay, so I think that we can do in this way. Okay, guys, from the web, I suggest you try to doing this. Meanwhile, I have to see also on the other guys in the room. So I will be open the lesson, but I think it's good to stop the recording just because there is no sense. And if there are any other question or problems, you can write to me. Or here during the lab, you can write typing on the chat and I will try to help you. License is on this link. You have to create an account and you're able to go to authenticate your account, and then you can use Microsoft Authenticator, then go again on the Intel page and download it. Guys, before you leave, I truly suggest you to download everything before the other labs. Just this, okay? Wait a minute, I just set up here and then I come.